unfortunately, I had to cut my beautiful introduction that I had thought out since I want to give Ivan the space to actually show his beautiful research, but I will list following. He has completed his undergraduate studies and also his master's in Lvov in Ukraine. After that, he completed his PhD in Kent University, Ohio, in US. He was postdoc at Liquid Crystal Institute at Omicron and at University of Illinois Urbana-Champaign. And since 2007, he has been a group leader of experimental lab focusing on soft matter at CU Boulder. He has received national and international recognition for his beautiful work on liquid crystals. He has been named APS Fellow, as well as, for example, Alexander Humboldt Stiftung Fellow, and many, many others. The list is long. His research focuses, as I said, on soft matter, especially on liquid crystalline systems. And this work that he's going to show you today, I find particularly exciting, and I have to admit, spoiler alert, I saw this talk 2 weeks ago at the Gordon conference. I was super, super excited. That's why I tried to convince him right away to come here and to share it with you, because it was just mesmerizing. So what he will show you is how you can actually, with experiments with liquid crystals, study and probe mathematical theories and topological theorems, and actually visualize them with real experimental data. So I found it really, really beautiful. You're in for a treat, so I think it was worthwhile waiting. Please enjoy.
Thank you. I promised I will finish by 5 p.m., but Colorado time. All right, so let me start from acknowledging students and postdocs who did most of the work I will present today. You see them here. Let me give you a brief historic interlude to the problems I want to discuss with you today. So long ago, was saying that if you were to have a knot in field lines, like magnetic field lines, and these could not cross each other because of, say, energetic reasons, then this type of knot would behave like a particle, right? And the knot ideas were exciting many physicists. Also, Kelvin, Tate, and Maxwell were thinking about knots as models for atoms. Long ago, of course, before people even universally accepted the concept that the matter is made of atoms, right? Of course, later on, we understood that atoms is something different. They are not really these, so under the idea, the different chemical elements would be different knots in these tables, right? In the tables of knot. And although this turned out to be not the correct model, right, but the idea excited mathematicians, and this was the origin of the mathematical knot theory. Many, many years later, physicists benefit from the knot theory, but at the same time, we also contribute to its understanding. And you might know that, for example, Ed Wheaton is the only physicist who got the Fields Medal precisely for contributing to understanding of the concepts in knot theory on the basis of quantum physics, right? So there is a lot of excitement as you look at the people whom I just showed working on the knot problems, and we got excited too, but in our case, we will use liquid crystal molecular alignment fields as a media in which we will realize these knot field configurations. So as you may know, liquid crystals stand in between the crystalline solids and isotropic fluids. They do have orientational ordering, but at the same time, they can flow. And so although it would be hard to, for example, knot an optical axis in a solid crystal, we can do this in a liquid crystal medium. And in fact, the director field in here is an optical axis, and it's something in which I'll be producing knotted field configurations today. So we'll discuss with you knots in molecular alignment field, knotted vortices, and solitons, and we'll start from the interaction between topologically non-trivial surfaces and the field configurations. And before we do that, let me describe you how we produce knot-shaped and other kinds of colloidal particles that are only micrometer or so in size, but have these elaborate shapes. So for this, we use kind of a fancy version of a 3D printer, where we use a femtosecond laser source to cross-link polymer originally as a monometric fluid in a tiny spot where we focus this femtosecond laser to. And then, because of nonlinear multi-photon absorption, 3-photon in our case, we can cross-link this polymer in a tiny spot in the sample. And then as we advance this focused laser beam, we can print different kinds of particles. Like, for example, these torus knots that you can see in here, which we can mate in overall dimensions of couple micrometers, so they are colloidal objects. Then what we do is we immerse these particles in the uniform far-field background of the liquid crystal, and then using nonlinear optical microscopy, we study the patterns of the molecular alignment field. Right, so in here again you can see a setup that allows us to do this, where on the basis of multi-photon absorption-based fluorescence, which is polarized from these types of building blocks of liquid crystal, we can reconstruct the three-dimensional patterns of molecular alignment fields.
Could you go back? You talked about polymers and you talked about liquid crystals. What exactly is this little green picture?
So when we polymerize these kind of particles, right, you have a monomeric fluid that's consisting of chemical units that can be linked to each other upon exposure of light, right? And this is driven by photopolymerization, where we have a photoinitiator that allows for this reaction to happen. So essentially,
I didn't ask how you manufacture it, but what is this? This is a it has many atoms each.
Yes.
And it's a polymer or a liquid
It's a
crystal?
polymer. Yeah. In here it's a polymer, and then we take this polymer particle and put in liquid crystal.
Into the liquid crystal as a medium.
Right.
But this is just a kind of a set of polymers
Yes.
that are together to make a string.
Absolutely. Yes.
Thanks.
Thank you. All right, and so now we will study how this molecular field alignment adopts around this type of colloidal particle. And so an example of three-dimensional structure that we can probe with this multi-photon absorption-based polarized fluorescence microscopy, we can, for example, reconstruct the patterns around these point singularities that you can see here on the basis of imaging polarized luminescence from such molecules like pentyl cyanobiphenyl here, because
I don't understand what's being represented and what points in what are the black lines the polymers?
The black lines are the molecular alignment field lines, right? So when I was showing originally this type of liquid crystal in here, right? In here you can see it having uniform alignment. But I mentioned that you can deform it, right? Because it has fluidity and order at the same time. And so in this case, this molecular alignment, which is depicted with the help of the black lines, is forming this three-dimensional texture that we can image.
The director field.
Right. All right, okay, so now, we'll see that these types of three-dimensional complex structures of point defects and also line defects and other field configurations we can image in 3 dimensions. And so in my talk, I will deal not only with point defects of this kind where the molecular alignment is disrupted at a point, right, but also with line defects, 2-dimensional defect lines that in here would be perpendicular to the screen, and those are the regions where, again, the field orientation cannot be defined, right? So it's singular in these cases. Now, in liquid crystal, we can have line defects with the quantified by the strength of winding number, S in here, that describes the number of times that the molecular alignment field is rotating as you would navigate this type of singularity once, right? So as you go around by 2 pi, you see the director here rotated by 180 degrees. So the ratio is 1/2, and that's the winding number.
Where do you get 180 degrees?
So if you
60 when you go around.
no, if you follow these lines, you will see that this is just 180,
It's going from up to down.
right?
Go 180 degrees and see that it's rotated by 90. That's the...
Way to see it, yeah.
Goes
And then
this way.
here, right, and then
Is that
here.
arrow perpendicular to those black lines?
Right.
Is that the point? Is that when you
No,
move it along
the arrow
circle?
is showing your navigation direction, right? So you are on this circle and you're going around the defect by 360 degrees, right? On the circle, and you notice that the director rotated by 180 degrees, right?
I don't see that because
Well,
I don't-
so-
you're not actually moving it around, so I can't.
Okay, so as I go from here to here, I rotated 90 degrees and then 90 more as I go back.
Perpendicular.
And it's total 180. So the ratio of 180 to 360 is 1/2.
All right.
So half integer defect line. In this case, as you would go around a similar circle, you would notice that the director is rotating in the opposite direction by 180 degrees. So minus 180 divided by 360 gives you minus 1/2. Well, in these cases, it would be 1 or minus 1. And so,
Is there a significance to the different color dots? You had some blue and some yellow and some white?
just this, the significance is that they have different winding numbers, but yeah. All right. Okay, well, and so now let's recall something simple from topology and something very generic, which is that when we would try, for example, to comb hair or vector field on a surface of a sphere, we would not be able to do it, right? And the reason is described by the Hairy-Bolt theorem, saying us that we inevitably have a singularity on the surface field of this kind. Indeed, as you would rotate around the sphere, you would see the singularity in here. And the generalization of this theorem to other kinds of surfaces is given by Poincaré-Hopf theorem, which relates the genus of the surfaces, 2-dimensional surfaces, or also Euler characteristic, which is related to this genus, with the types of defects that you would expect in this case. So Euler characteristic is 2 minus 2g, where g is genus, and genus is essentially the number of holes in a continuous 2-dimensional surface, right? So then these are the Euler characteristics, and what we note in here that unlike for sphere, in the case of a torus, you would not expect to have these surface singularities to appear. But as we put a torus-shaped colloidal particle into liquid crystal, we immediately notice that some singular points emerge in here, right? And so there are 4 of them, right? You might be surprised. Maybe in liquid crystal topological theorems fail, don't work. Or what really happens? Well, so to know what exactly happens, we do this nonlinear optical imaging with different polarization of excitation of femtosecond laser light. And from that, we can deduce the patterns of molecular alignment field on the surface of such particle. What we notice then is that out of the 4 defects, 2 have positive winding numbers, 1, and 2 have negative winding numbers. So the liquid crystal finds its way of satisfying topological theorems, but in a different way, by having self-compensating singularities on the surface of these particles, right? Now let's look at other kinds of particles that we can again produce and put in liquid crystal.
Particle, is that the whole torus?
Right.
That's a particle.
That's a particle.
Okay.
And also, when you say liquid crystal, you mean nematic.
Right. In this case, it's nematic, yeah. All right, and so now as we put handle body with genus 2, so you can see in here 2 holes, right, we see more defects, right? And again, they do satisfy the topological theorem, because as we study in detail these types of charges, we see that we have 6 negative surface defects and 4 positive, and they add together to the Euler characteristic of this type of surface, right? And in fact, as we study this type of interplay between the field of the liquid crystal and the surfaces of such particles, we know that it always happens so, but pretty much always in a way that you could not guess right away. Because what we have always, as you can see from this table, that for different handle bodies with genus and Euler characteristics given in here, we have combinations of defects with plus and minus charges that add together to the Euler characteristic, as you can see in here, right? All the time, right, never failing to obey this rule, but at the same time they have many ways of doing it. These are just examples, right? So in other words, the interplay between the topology of the surface of colloidal particle and that of liquid crystal is richer than we would simply guess on the basis of what topological theorems tell us, right? But at the same time, we always see these theorems obeyed. Yes?
So maybe it's where you're going, but I mean, in the hair, combing the hair and everything, you're thinking about some like vector field on a surface, but you know, the liquid crystal, from my understanding, you're thinking about it on the surface of this thing, so, but that's not the only thing that's going on. It's sitting in a vat of liquid crystal, so it's embedded in a 3D thing, right? So we haven't seen, I don't know what the generalizations of these theorems are, but it could be that it's totally natural that you get all these double.
Yeah, and it's just the fact is that you see these theorems do not predict, they put a constraint on satisfying this sum in here, right? But then what are the ways of realization is precisely this, right? For this.
I mean, your starting point is already bigger than what those theorems were.
Mm-hmm.
That it's more than just a vector field on the surface.
Right, yeah, and so I'll come to this point as well, that what we have in here is also a line field, right, rather than vector, and that enriches this type of interaction quite dramatically.
So maybe a related question. So if the topology is correct, if you change the shape from a circle to an ellipse or any kind of donut, you still must have the same topology. Is that correct? Or is it sort of connected to the media and the symmetry?
You mean the topology of surface or topology of the host medium?
I mean, if the genus is 1, it doesn't matter how you distort it elastically. But I guess all your shapes are very circular and very symmetric. So if you make it slightly asymmetric,
Right.
will you see the exact same difference?
In terms of the topological charges, you will see them adding to Euler characteristic, but the locations will be different, So there will be some details that, of course, will be different because of geometric shape modifications and so on.
But they never annihilate the defects. The defects of opposite charge.
The defects of opposite charge in these cases can annihilate, and in fact you can have transitions between these states. Like, for example, you see for genus 1 you could have either 4 defects with 2 of them being +1s, 2 -1s, or no defects at all, right? The way to transform from one state to the other state is to, in this case, rotate the particle, right? But the key point that I want to make in here is that the molecular alignment field interacts with the topological and non-trivial surface to satisfy these topological theorems in a way that cannot be predicted, right, or purely from on the basis of topological constraints, right? They come from the reasons of minimization of energy in the liquid crystal medium. All right, so now what's also interesting is that because these defects on the surfaces are in the molecular alignment field, which is non-polar, right? So head and tail are the same, so it's a line field. We also observe that these point singularities split into the ring-shaped structures, as you can see in here, right, which would not be allowed in the vector field, because if you would have vectors instead of these lines, and you would go around such a half integer line in here, you would have a singularity, right? So, and that's an interesting peculiarity of the line fields, because as you can see, when these topology satisfying surface defects emerge, they give rise to handle-shaped topological defects on the surfaces of the colloidal handlebodies that we study in here. And this is, again, a peculiarity of line field that would not be possible in the case of vector fields. Now, we can also have colloidal particles with perpendicular surface boundary conditions. And in this case, the predictions of topological theorems relate to the bulk defects, not the surface defects on the colloidal particles. Again, topological theorems state that the net charge of the point defects in the bulk should add to chi over 2, where again chi is the Euler characteristic of the surface of these colloidal particles. And in here again, it's interesting that the ways these topological constraints are satisfied is not the simplest one. It's the one that's minimizing the overall free energy of the liquid crystal. So for example, as we insert a ring-shaped particle, although we would not be required to have topological singularities at all, instead we have point defects with self-compensating charges +1 and -1 adding to 0, right? And then as we have the handlebodies with genus 2, again, we satisfy this topological constraint, but through having the self-compensating defects, right? So we see that already when we have the simplest objects of knot theory, which are unknots in this case, rings and so on, we have this interesting interplay emerging. But the question is, what if we now immerse knotted particles? What kind of interesting things can happen? And so these, as you can see in here, are torus knots that are classified on the basis of 2 numbers that tell us the number of times that you would go around the torus, around the straight axis and the circular axis, right? Those would be these two numbers. For these particular examples I'm showing you in here, they would be 2 and 3 in this case, right? So you go around the axis of torus 2 times and 3 times around the circular axis, right? So we can make them again with well-defined shapes as colloidal objects with couple micrometers in dimensions, and then we immerse them in liquid crystal. So what should we expect in terms of generation of topological defects when we put these particles into the liquid crystal? So what's the Euler characteristic of such objects? Well, it turns out that Euler characteristic of a torus knot is always 0 for all of these structures I showed you, like the pentafoil and trefoil knots. And you can see it when you, for example, would cut such a knot and then reconnect it back to a ring, right? So when you do cutting and then gluing back, topology of the surface is preserved. And so you can see indeed that that's similar to a ring which has Euler characteristic equal to 0. So now when we put, however, these types of torus knots into liquid crystal, you can see them generating surface defects when the particles' boundary conditions are tangential. You can see them here in a polarizing optical microscope and also just in the bright field microscopy observation on the basis of light scattering. Then we can reconstruct the three-dimensional field configurations and the patterns of molecular alignment field, which in here is shown using these colors, which essentially code orientations, azimuthal orientations of molecular alignment field. And the points at which these different colors meet are the surface singularities, these point defects, right? So as you would rotate this particle around and count them, you would realize that although we did not have to have defects in here, we do have them. And in fact, we have 6 plus ones and 6 minus ones on the surface. That's consistent with having 4 Q knots. Remember, Q is the number of times we go around the circular axis for the torus knot. The same thing is true when we take a pentafoil knot of this kind. And again, we see all of these point singularities emerging on the surface. And in this case, we have 10 plus ones, 10 minus ones. So total number is 20, and that's consistent with 4Q. Again, Q is the number of times you go around the circular axis in this case, right? Well, what happens if we have instead perpendicular surface boundary conditions? Even more interesting stuff, because in this case, we generate a vortex line in the bulk of the liquid crystal, and in fact, 2 of them, as you can see them in here, propagating along the surface of this tube that forms the, in this case, trefoil knot in liquid crystal. And we have 2 of these defect lines. You can see them, for example, on the basis of nonlinear optical imaging, and here are these dark lines, which we can trace in 3 dimensions. And what we observe is that these half integer lines that I was introducing to you in the very beginning of talk, in fact, follow the torus knot tube and form their own knots, trefoil knots. Moreover, these trefoil knots are linked with each other, as you see depicted in here, and with the colloidal particle knot at the same time, right? So I think that's interesting that the knotted particle generates knots in vortices in liquid crystals, and these all knots are linked with each other. But we can also make colloidal particles that are linked with each other. So not just rings, for example, or knots, but also rings that are linked with each other. And so in here you can see the different types of bright field microscopy and luminescence-based imaging in 3 dimensions of such links. So in this case, it's a Hopf link where they are linked just once. And in this case, it's a Solomon link where the 2 ring-shaped types of colloidal rings are linked with each other twice. All right, well, so what happens as we put them in liquid crystal? Of course, as you have them in water, they undergo Brownian motion, rotational and translational diffusion, but they cannot leave each other because they are linked, right? And so in liquid crystal, they align with liquid crystal far field, and under thermal fluctuation, both the relative positions of the 2 linked rings and orientations are jiggling in response to thermal energy. So again, we can image them using nonlinear optical microscopy and reconstruct the field configuration around them. And what we see is that, again, because the rings have Euler characteristic equal 0, they would not have to form singularities on their surface, right? Even when 2 of them are linked. But in fact, in this case, we see 8 self-compensating surface defects that are not required, but in liquid crystal, to minimize free energy actually exist, and you can see in here taking place. Now, as we produce perpendicular boundary conditions, we instead can again generate the vortex lines that form closed loops on the surfaces of these particles. And you can see in here depicted as these red strings on the basis of our experimental reconstruction and numerical modeling, which agree with each other. So you can see that these line defects can jump from one ring-shaped particle to the other and essentially further interlink them. And as you would then depict in here the colloidal rings with blue and yellow colors, then show the red rings corresponding to the defect rings, right? You can see that they are all interlinked with each other in a pretty complex way.
Can
Yeah.
2 defect rings join together to become 1 defect ring?
It isn't, in fact, possible. We can tweak those things with laser tweezers, yeah.
And then what would be the topology of this combined single ring? Will it be a trivial knot or trefoil or what?
It will depend on the geometry. The landscape of those things is very rich. So I'll show in a minute a couple examples of, that we can generate when we have these colloidal rings linked with each other, but then we have multiple different configurations for defect rings, right, that can exist.
When you talk about the boundary condition, this is of the director at the boundary of the colloid, right?
Correct.
And that's controlled by chemistry?
That's controlled by chemistry and the material composition of the particle.
Well,
so if you,
chemistry.
so if you have different polymers, they would give different
Right,
boundary
that's
conditions.
what I mean by
Yeah.
chemistry. Right.
All right. Okay, so I mentioned just a minute ago that there are multiple ways for these defect rings to interlink, and here's another example, right? This is from experiments in the regular polarizing microscopy observation and in nonlinear optical microscopy, and you can see that here's yet another example where 2 of the defect rings are linked with colloidal rings, but one is not, and in fact, we could pull it with laser tweezers away. Right, here's yet another example of a Solomon ring of a Solomon link of 2 colloidal rings, right? That we have in a liquid crystal, and in this case, again, what we see is that these defect rings are following the colloidal rings in a rather complex way and all interlink with each other, right? So now what's interesting is that, for example, when we have the Hopf link of two colloidal rings and we put it in liquid crystal, it's not just one structure that emerges, right? There are many of them, right? We have in all of these examples I show in here that we reconstructed from experiments and also seen in numerical modeling, we have only one type of colloidal object, which is two linked rings. But the defect rings do all of those crazy things, right? And so you see them in these diagrams depicted as red rings corresponding to defects, and also in the in these graph representations where every ring is shown as a filled circle, right? Red corresponds to defects, and the blue and yellow correspond to particle rings. And whenever we have black edges, they are linked with each other. Whenever we have no black edges between them, they are not, right? And so you can see that all of these configurations can emerge and have and be stable for a long time, right, in a liquid crystal medium. So what this tells us is that in molecular alignment nonpolar director field, the manifold of structures that can satisfy the topological constraints is very rich. It's much richer than what we would have for vector fields, for which we have very precise predictions of the topological theorems, right? Because, in fact, none of these defect rings could even form in the vector field. They are simply not allowed, right? In a liquid crystal molecular alignment field with nonpolar symmetry, they can exist, and they allow us to see all of this type of linking, right? Well, so before I slightly shift gears with discussing with you a very different type of knots, I would like to again give you a historic interlude. We already discussed that Kelvin proposed a model of atoms as being knots, right? These kind of ideas resurfaced again after the Second World War when Heisenberg was thinking about elementary particles and their nature. And he was thinking that maybe they are some types of knotted solitons that are protected by topology and localized in all three spatial dimensions, right? Well, very soon, Derek was able to show from some scaling arguments that because of energetic reasons in a simple sigma model in high energy physics, this should not be stable energetically, right? But Skyrmy and Fadeev were able to overcome these constraints of Derek's theorem by adding nonlinear terms to what became nonlinear sigma model, right? You know, these ideas of non-singular topological solitons, which essentially would be just like the Gauss knots, right? Some knotted field configurations that are non-singular but cannot be eliminated because of knotting, right? Topological protection. And so, of course, later on in high energy physics, quantum chromodynamics was invented and became the way of describing and understanding elementary particles because, as you may know, probably the original Skyrmy model was a way of understanding elementary particles with different baryon numbers, right? However, Ed Wheaton was able to demonstrate that there is a relation between the original Skyrmy model and the quantum chromodynamics. And in fact, there is still a lot of very active research going in high energy physics that's looking at these not soliton field configurations. Nowadays, however, you probably know about Skyrmions in condensed matter physics, right? So they derived their name from Skyrmi, who was a theorist in high-energy physics. And they are, however, and there are many other fields, like liquid crystals, for example, where we study this type of solitonic field configurations. So what I will discuss with you today is realization of such topological solitons that were exciting the field of high-energy physics for 2 decades or so, now in liquid crystals and colloids, right? And I mentioned to you that Skyrmions are studied in hard condensed matter, in chiral ferromagnets, for example. But however, these are two-dimensional analogs of the Skyrmi solitons, right? So they are often, for that reason, called Baby-Skyrmions. What I will discuss with you today is real three-dimensional solitons, or grown-up Skyrmions. But let me start with the idea, of what is a Baby-Skyrmion, or two-dimensional topologically protected but non-singular field configuration. So as you look at this type of a spin texture or magnetization field, you see it's totally non-singular. It's continuous everywhere, right? There is nowhere that you could not define orientation of the spins. At the same time, it's topologically non-trivial because you cannot wiggle these spins and eliminate the structure no matter what you do. And this is consistent with the fact that as you would map this texture to the order parameter space, which is a two-dimensional sphere for this type of system, you would cover it completely, right? And in fact, the number of times you cover this order parameter space is the Skyrmion number, the topological invariant for these systems. Now, what would be a real grown-up Skyrmion? Well, for that, to introduce you, I need to remind you the concept of preimage. The preimage of a point on the order parameter space is a region in three-dimensional sample within which spins or magnetization or director would all point in this very same direction, right? So all possible orientations can be represented as points on the sphere, right? And therefore, we can describe all regions in the space as corresponding to these points on the S2 sphere, right? Which would be pre-images of this point, right? Now, for you to have a not soliton, the Skyrmi-Fadeev kind of soliton, you would need to have every point on S2 sphere having a preimage in the form of ring, right? Or unknot. These rings corresponding to different points would have to be linked with each other. And that linking number would have to be the same for all combinations that you could come up with, right? And moreover, that kind of structure would have to be embedded in a uniform far field, right? Because this structure has to be localized in all three spatial dimensions. Well, you can say it's maybe way too much to ask for something like that to happen, but we will see that we do realize these kind of things in real experimental systems. So what we use in this case is a colloidal fluid ferromagnet, which is a liquid crystal made out of molecules just like the ones we use in displays, right? But doped with colloidal nanoparticles that are, in our case, barium hexaferrite nanoplatelets, which are magnetically monodomain. And what's interesting is that these nanoplatelets spontaneously form a ferromagnetic system, right? So they all line up with their normals parallel to the molecular alignment field, director field, right, and in the same direction. So they essentially convert our system into a polar medium, right? And you can see that this is ferromagnet when you, for example, probe the magnetization hysteresis loop. It's just like what we also know for solid ferromagnets, right? But in this case, the platelets can move around within the medium and the molecules move around, so there is fluidity and this polar ferromagnetic ordering combined at the same time. Now, in addition, we add a chiral additive, molecules which lack mirror symmetry and therefore want to induce twist within this type of medium, and then we confine such a material between substrates with perpendicular boundary conditions so that the uniform twist is not compatible with these boundary conditions and you have some form of frustration, right? Now, as you look at the samples that you got in this case, you have a lot of different bright structures that are localized when you look between two cross polarizers, right? And this medium is optical anisotropic, so it tells you that, well, there is some field configuration that's maybe non-trivial, maybe interesting. We need to study to see what it is, right? And in order to understand whether that's something interesting, we need to do an analog of what mathematicians call Hopf map, right? So what this is we take every single point on the S2 sphere or the parameter space and look in our sample in both experiments and in numerical modeling to see where are the regions within which magnetization points in that direction, right? So as I already mentioned, we do it then for all points on S2 sphere, and this is an analog of the Hopf map. Now, as I mentioned, we do it in also numerical modeling, where we minimize first free energy in order to obtain field configurations that should be realizable because of being of local or global minima of free energy. Now, those of you who might be working with solid ferromagnets would know that for chiral solid ferromagnets, the simplest model describing this system would have free energy in this form in here, where the first term is called exchange energy term, right, and A is exchange constant, and the second term is Dzyaloshinski-Moriya term, which is a chiral term. And in our liquid crystal ferromagnets, however, we have a little bit more complex description, where we have three different terms in here describing highly anisotropic ways of deformation of this magnetization field. However, within one constant approximation, we can relate those two things with each other, right? So in fact, these three terms transform into this one when we assume that these constants are equal and also these relations between the constant, right? So these two expressions, in fact, in one constant approximation are equivalent to each other. And so, and therefore, in our numerical modeling, we do work with both the one constant approximation and the real case where we have three constants different. Now, as we minimize free energy on a three-dimensional grid, starting from some random original pattern of spins, right? Then we obtain localized structures, and then here you can see free energy density isosurfaces that show that within this structure, somewhere here, we have energy being minimized, right? Because we will see in just a little bit, that's where the magnetization is twisting, right? And so, indeed, as we plot this twist term or handedness parameters, we call it, corresponding to the Dzyaloshinski-Moriya term that I was showing you, we see that within the region of this localized structure or soliton, there is a lot of twisting that has handedness matching the handedness of the chirality of additive that we add, right? So what this means is that formation of such a soliton allows you to embed a twisted field configuration locally, and that way relieve the frustration that you have because of boundary conditions being incompatible with uniform twist of magnetization, right? And so what are these structures? Let's look at them in more detail. So as you would look at this structure in the plane perpendicular to the magnetization, far field magnetization, in the middle of it, you would see that this, the magnetization is twisting by 360 degrees in all radial directions, right? Continuously, no singularities. And then as you look in the plane containing far field magnetization, you see that it's also embedded in this far field background without any singular defects. It's totally continuous, right? However, now as you would look at pre-images of this kind of field configurations, you would see that for all points on S2, they are closed loops, right? So I look at every single point and I see they are closed loops. Moreover, as I take two different points, I see they are closed loops linked with each other, right? So same number of times the linking number is conserved. Now, as I would go from south pole in here of the S2 sphere to the north pole, what I see is that when the polar angle is constant, I essentially tile these pre-images into tori, and then I nest these tori one in the other, all the time increasing the size of this tori until I get to the north pole, which is then confining our entire solitonic structure in the uniform far field background, right?
You cover torus in one layer of this process. You have a torus knot or what?
Yeah, those are all torus knots. Yeah. So
What are the
they are. We will discuss this. They are all tori knots of pre-images, right? Of the regions with the same orientation. Yeah.
But what chooses their P and Q?
That we will discuss, because I will in fact have examples of very different configurations with different P and Q, right? So it's energetics. Those will be different energy minima. All right, and so let's look at it more, right? So here is our south pole pre-image, just a ring. I go, I change my polar angle, I get this nested tori, and they all confine eventually into the north pole pre-image that's corresponding to the far field, right? And the pre-images in here are all linked the same number of times. Now, on the basis of this modeling, we can predict what our 3D optical images should look like in the planes perpendicular to far field magnetization and orthogonal to them, right? And here we have for two soliton structures, and also for different polarizations of excitation light, linear and circular in these cases. And as we take these images with an actual experiment, you can see that they very closely match, right? Those are experiments and those are numerical models. Again, theory, experimental, right? Now we can also directly compare pre-images, and then here you see a pair of pre-images generated on the basis of numerical modeling. This is experimental analog. Again, they don't only just agree in terms of topology, but even geometric features that you can see in here are similar, right? And that we can do then for all pre-images and unambiguously prove that they are exactly the structures we were, hoping they would be, right? However, there are many kinds of solitons. For example, some would have pre-images that are closed loops, but not linked with each other. Like in this case, right? So again, we have pre-images that are closed loops, but they are not linked with each other. And this is the type of structures that we also realize. Now, there are also pre-images that would have opposite linking number, like in this case I was showing you, right? So the linking number in here is -1, in the previous case was +1. Now, what you see in here is yet another structure that has linking number equal to 2, and so far you're looking just at one pre-image as it changes as you go throughout the sphere, right? There is some critical angle at which the pre-images transform, but as you then look at pairs of pre-images, like in this case, you can see that the linking number is always conserved, although the way you link those pre-images is changing as you go around this, the points on this S2 sphere, right? So you can see that the linking number is always 2, but the structure, right, has a combination of these ways to do this, accomplish this link, right? And so now we can also have such solitons combining with point singularities, like in this one, the points at which these pre-images terminate are singular defects in here, right? So we essentially can form a hybrid structure, which we call torons, right, where we have Hopfian soliton with well-defined linking and Hopf index coexisting with self-compensating point singularities of this kind, right? And there is really a large diversity of structures, right? So in here, for example, you see the tori that would correspond to this type of soliton when you have constant polar angle. So this would be corresponding to a set of these pre-images with a constant angle, right? Very beautiful topology that we uncover day after day something new, right? And in fact, this is our table of knots. Remember, Kelvin and Maxwell and Tate had their table. We have our own too. These are the types of knot solitons that we discovered. And the simplest ones, which I was showing you, would be just 2 rings, right? Or in terms of graph presentation, they would be just 2 filled circles connected with one edge. Well, you can appreciate the diversity of structures and complexity that we actually can realize in these systems. So what are these types of structures of field configurations? How should we understand them? Well, let's go back to Baby-Skyrmions, right? Those were 2-dimensional field configurations that I was telling you are 2-dimensional solitons. These can be described as elements of the second homotopy group, and in fact here should be pi 2 S2, right? And you can understand why, because using stereographic projection from 2D plane you can map to sphere, and from sphere back to 2D plane, provided that your far-field background is uniform, right? You can represent everything on 2D plane also on the S2 sphere and vice versa, right? And so you can morph these structures smoothly back and forth without changing topology as you go either on S2 sphere or in the 2D plane, right? So now, because it's so, and in fact, although these are 2-dimensional solitons exist in a plane, right, they also exist on S2 sphere, as you can see, because these are equivalent, right? So now, for you to know how you should describe them in terms of homotopy theory, you would need to map from S2 sphere to the order parameter space, which is also S2 sphere, right? Which then makes all of these structures elements of the second homotopy group. Right? Now, in our case, when we have the structures emerging in 3-dimensional space, it's R3, as mathematicians would call them. And also, for the far-field uniform background, that's equivalent to S3, right? So I have no way of good drawing for S3, 3-dimensional sphere in 4 dimensions, right? But that's representation for it in here, right? And so what you would need to do now is to map from S3 to S2, right, to assign homotopy group to these types of structures. And in fact, that's something that corresponds to the Hopf vibration, and the ways of doing this correspond to different elements of the third homotopy groups, which describes the maps from S3 to, in our case, because order parameter space is S2 to S2, right? So this is pi3 S2 homotopy groups, and all the structures that we saw are elements, integer numbers corresponding to this group of maps, right? And so, so as I already mentioned, the simplest element is nothing else but celebrated mathematical Hopf vibration. And the so in here you can see a table describing the maps, topology of maps from spheres to spheres, right? So when we have a map from the S3, right, to the S2, this is the element corresponding to the third homotopy group of such maps. And when we have these types of pre-images that are linked with each other, the linking number is the topological invariant, the topological number that tells us how these pre-images are linked. And this corresponds to an integer number corresponding to this group. All right, well, so you can see we can realize them. They can be stable, these types of solitons. But what we can do, the exciting thing that they are in the media that are highly responsive to external stimuli. So, for example, in this chiral ferromagnet, colloidal ferromagnet, we can apply magnetic field. And so you can see these localized structures in here viewed between cross polarizers. And as we apply field in two opposite directions, either parallel or anti-parallel to far field magnetization, they shrink or expand. Now, these are just individual structures, but when we have them spontaneously under well-defined condition assemble into periodic arrays, like this array in here, we can also see this happening, right? So the structures morph, right, and interact with each other, and yet they are stable. You see them not disappearing. The reason is because they are like these Gauss knots, right, that are protected by this topology, and although you can morph them, you cannot easily have them go away or change. Although we can make them change if we apply even stronger external field, right? And so in here, in fact, is nothing else but what we could call, in quotes, a phase diagram of this kind of knotted phases in two-dimensional case like the one I was showing in here. And so you can see as we apply magnetic field, fairly weak magnetic field, we can go through a series of these different structures, right? And the video in here shows just one of them for this case, right? So a very rich kind of behavior where we can morph these structures continuously, first without changing the linking number or Hopf index, and then as we apply even stronger field, we go through this quote-unquote phase boundaries where the linking number changes, the Hopf index changes, say in this case from q equals 0, right? So although these are knots, but the linking numbers add to 0, to -1, to 0, and so on, right? So very rich behavior. Now,
could you go back?
Yes.
You have different behavior for positive and negative magnetic field, but what sets the sign of magnetic field? Is it the direction of magnetization in the far field?
Absolutely. That's the case, yeah.
I see.
Yeah.
So it's against far field magnetization.
Absolutely, yeah. All right, and now we also can apply electric fields, and the host, as I mentioned, is liquid crystal. So in our displays, we switch liquid crystals with 1 volt or so of electric field. While in here, we can also switch liquid crystal ferromagnet with very weak fields. And so you can see in here the type of switching that I demonstrate, how these structures transform. And the field is changing very little, as you can see. So first you deform continuously, but then there are some abrupt changes during which Hopf indices change in here as well, as we characterize them on the basis of numerical modeling and nonlinear optical imaging. And so you can see that we can transform these configurations in dramatic ways and change indices, or we can have them transforming continuously while the Hopf index is staying the same, right? Now, even that was not all. We already were pretty excited that we could see so much of this behavior happening. But then when we started applying these electric fields, what you see in here is that the far field background is changing this field, right? So the soliton has its localized structure that's very complex, but it has to morph to comply with the far field. And you can see this happening in here under these small voltages, and as it's matching the far field, which is tilting with respect to the original orientation. But as we then modulate this field, right, so say electric field is 1 kilohertz, but we modulate it, so carrier frequency 1 kilohertz, but modulation frequency changing from hertz to 100 hertz, we see that these localized structures can actually swim. They behave like active particles, right? And moreover, you can reverse the direction of motion by changing the frequency of modulation without changing carrier frequency, right? And so why does this happen, would be a question as well. Well, we can see that within these fields, the topology does not change, right? But the structure morphs dramatically. And in one case, you apply field, you have electric torque changing orientation of this director locally within the complex structure in asymmetric way, right? And then as you turn off field, this torque does not exist, right? So it's only elasticity of liquid crystal ferromagnet that's driving it back. And because of this difference in balance of torques, you have asymmetry in response. And as a result, these structures move in one direction, right? And so we, in fact, can model this behavior numerically, and you can compare experimental images with numerical results. And the way we understand this, it's actually relating a little bit to biology. In biology, in many cases, we can have Skyrmion motion or Skyrmion surface waves where you can advance because of non-reciprocity of these surface waves, right? And in here we see something similar, although this is in this localized knotted field configuration where we squeeze electrically this twisted region in a symmetric way, and then it's bouncing back much faster, and as a result, the overall field configuration moves forward without, because of this rotational dynamics in the field configuration, right? So
reversible in which sense? Thermodynamically reversible?
So reversible in the sense that you see in here velocity is positive and negative. As we change frequency, we can move it this way or that way. So the motion direction is controllable.
By frequency?
By frequency. And the reason is because, there is this asymmetry in dynamics of response of the field configuration to on time and off time, right? Because of different balances of torques, right? And now that timing can be depending on how this response time compares to the oscillation of modulating field, you can move one way or the other way. So because, do you see what I mean?
But from thermodynamic point of view, if it moves in one direction, somebody has to perform work.
Absolutely, yes. And the way you should understand this, you have electric field applied globally. That electric energy is transforming to elastic energy because you are squeezing this field configuration to a state that it doesn't want to be. Then you turn off field and it springs back. And because, you know, this is not just simple reversal the way it does, right? Because of the asymmetry in the torque balance, it moves forward or backward depending on the timing of modulation.
Detail balance because it goes back in different paths.
Absolutely, yes. It's just like so in the Skyrmion waves, you know.
The source of energy is the source of change in electric field.
Absolutely, it's electric field energy that's transforming first to elastic energy and then into motion. Well, so this brings me to conclusions. So I hope I was able to show you that nonpolar molecular alignment fields can interact with surfaces in a richer way than vector fields do. I demonstrated to you that knotted colloidal particles can interlink with knotted vortex lines, again in a very rich way. We also can generate not topological solitons that can be stable, that are described as elements of the third homotopy groups, and we can have directional motion of such structures. Now, in the end, I want to say we are quite optimistic about practical applications of those kind of things, because if you think about our computer displays, iPhones, and so on, in all of these information display devices enabled by liquid crystals, you switch between two uniform states, right? So never topology comes into play. However, you can imagine that we can switch between all of these states, right? And that can allow us for bistable or multi-stable display modes where, you know, to display some information you would not even need electric power. Only in the case when you're switching you would need it. And moreover, in terms of these three-dimensional grown-up Skyrmions, they also should be realizable in solid ferromagnets because I mentioned to you that the simplest description of chiral ferromagnets is just one constant approximation of the free energy that I demonstrated, which would mean that they might be also realizable in solid ferromagnets. And in fact, we have a recent collaboration with André Thaville at Paris Sud, you know, with an effort to find them in solid ferromagnets as well. So thank you for your attention.
Questions? Andrew.
Can these potentially drag a colloid if you yeah.
Yeah, they can be used for transporting things, yeah.
So what determines the optimal, energetically optimal number and location of the defects on the surface? Is it like local Gaussian curvature involved and stuff like that?
It is involved, so what determines is minimization of free energy, right? And that gives you a landscape with many minima. And then as we study those things, for example, by heating up and quenching temperature, going order-disorder transitions and cooling down, we then can observe that some structures are much more frequent, so they correspond to lower free energy. The other are less frequent, and they would correspond to high energy, but still a minimum that, you know, we can observe of free energy.
Or maybe the ones which you visit more frequent correspond to
the driving, kinetic. Yeah, easier kinetic. That could be too. Yeah, yeah. But in some way we also perturb the system in different ways to kind of get an assessment of that possibility too. Because, for example, we can poke them with laser tweezers and so on.
Is there a real possibility for something like a spaghetti state where a system wants to be filled with these things as opposed to having them be sparse, and where they might define properties?
Which ones? Like the solitons?
The solitons, yeah.
Right. So yes. So there are these. I showed you some diagram, right? So there are these conditions where they the minimum of free energy under these boundary conditions. They are global minima. They want to be in this state.
But where they would be very, very dense, such that both properties of the system might even be influenced by it?
Yeah, absolutely. They were tightly packing those things. Yeah, so I mentioned that in solid ferromagnets they could exist too. There are in fact many structures that people don't understand, and they could be something of this kind. If it would be so, then in some of the chiral ferromagnets, they could be as small as 5, 7, 10 nanometers, right? Which could be really exciting for data storage, because you could pack them in 3D, unlike the current 2D skyrmions, right? That are very also promising for spintronics. There are these racetrack memory ideas as well. They could be also of interest for this. They're also topologically protected. Yeah.
Last question there.
So how sure are you that we have only one defect and not a cluster of them? But these systems are rather big, like it's 10 microns. So what is your feeling?
You mean one defect in which system? We had colloids.
There's like a sort of an endpoint, one dot, and then there are these other lines, the field lines, right? But in the system that we have is a big surface, and it's sort of you have this boundary condition that somehow forms this defect. And it could be multiple of them. It could be like 10 of them, 1 of them, 100 of them. In experiment, it shows as 1, I guess. But I'm just wondering, like, if you really zoom in, are you 100? Is there any reason that it should be exactly 1? Could it be 10, and is it still the same physics?
We can be sure because, these defects are not actually stuck in a place. They are undergoing Brownian motion. If you would look on the singular points, I think you were asking about, right? If you would look at this handle body, they're jiggling in here a little bit this way, that way. And from that dynamics, we can assure that that's the case.
So you think it's exactly 1?
Yeah. Also from the standpoint of view of the field configuration around it, right? That's very obvious.
Thank you. So let's continue this discussion with wine and cheese on 8th floor in soft matter conference room, and let's thank Ivan again. Thank you so much. Please follow now the crowd.